In section 12.4, we will be discussing about curvature and normal vectors of a curve. Now, on the previous section 12.3, it was discussed the tangent vector. Okay, so now if we're given any curve, any arc length s, and the tangent vector at any point is represented by this t that you see right here, then the derivative of the tangent at any given point, it's going to give us what is the magnitude or the length of the derivative of the tangent is going to give us basically how much the function is curving at any given point along the curve. So if you see on a straight line, let's say these are my tangent vectors. Okay, the derivative of the tangent vector right here, it is going to be 0 because the graph is not curving. Okay, so whatever the graph doesn't curve, that means that the curvature is going to be 0. Okay, now this is the formula for the curvature. We call it k, lowercase k, in terms of any given arc length s. But what if the arc length is given in terms of any parameter t? Then using what's called, we talked about the chain rule before in calculus 1. Then dt over ds is the same thing as dt over dt times dt over ds. And right here we can say that dt and dt, they can be reduced, and that leaves us with the derivative of the tangent with respect to the arc length. Okay, but we're assuming that we have a vector in terms of a variable, in terms of a parameter t. So we can rewrite it in this form, and thus if we separate it, this is going to be the following: the derivative of the tangent with respect to the parameter t times the derivative of the parameter t with respect to the arc length, but multiplying by the derivative of the parameter t with respect to the arc length is exactly the same thing as dividing by the derivative or the arc length with respect to the parameter t. So when if I move this to the denominator, it's gonna flip around, right? So this is an additional formula for the curvature. We can get the curvature if it is in terms of a parameter t would be, when I say the derivative of the tangent vector, I like to call it t prime with respect to t divided by the derivative of the arc length with respect to t. That's the same thing as the derivative of the position vector. So that would be the same as your velocity vector. So I call it r prime of t, the magnitude of that, which this is exactly the same thing as the magnitude of the velocity. Okay. And that's what we see on the next page. Curvature can also be found by, we can say dividing the magnitude of the derivative of the tangent vector with respect to the parameter t by the magnitude of the velocity, which is the same thing as the magnitude of the derivative of the position vector with respect to t. Now, then we also have a normal vector on a curve. Okay, the normal vector is a vector that will be perpendicular to the tangent vector. So once we have the unit normal vector, okay, then if we get the derivative of the unit tangent vector and we divide it by the magnitude of that derivative, it's going to give us the unit normal vector. And what is this vector going to be helpful on? It's going to help us to basically do one very important application of this section, which is finding the circle of curvature along a given curve. Okay, what does it mean by the circle of curvature? Let me just give you an example right here. Okay, you see that circle basically approximates how much the graph is curving, like this vector or this particle is curving at this point P1. Okay? At any point on the curve, the circle of curvature, just understand that it's going to be different. Okay? So, and what do you notice right here about this normal vector? That this normal vector that we see right here, it's going to help us to determine basically the radius of that curvature at that given point. Okay? So just remember that this n represents the unit vector. That doesn't mean that that vector just is going to represent the radius. It could be that that unit vector is going to be this long. So, and to get the radius on that vector, all we have to do is just remember what we did in one of the first sections of this chapter, is we multiply to represent a vector in terms of its direction and magnitude. We multiply the magnitude times the direction vector. So in other words, whatever normal vector we get, if we multiply times the magnitude of the radius, which in this case that magnitude would be the radius, that will give us the length of that radius on that circle of curvature. Now, something I mentioned to you is that the circle of curvature is going to vary depending on which point on the curve you're located. So for example, let's say I am located at this point on the curve. So you see that at that point on the curve right here, the circle of curvature, it is way bigger. Okay? So, and you see that the graph or the vector is curving less at this point than at this point. Right here, the curvature is greater than the curvature at this point. So, wherever the graph or the particle that is traveling curves the most, the circle of curvature is going to be smaller than anywhere on the curve where the particle curves or the least. Okay, so the greater the curvature, the smaller the circle of curvature that it's going to have at that specific point. The smaller the curvature, the bigger the circle of curvature that will be represented at that point in the curve. Okay. Now there's another formula to represent the normal vector. The normal vector, it is 1 divided by the curvature times the derivative of the tangent vector. But another way of representing the normal vector in terms of the parameter t, so it's just basically the derivative of the tangent vector divided by its magnitude. So this will be the best way of representing that normal vector. Okay. And this is, remember, the derivative of the tangent divided by its magnitude will be representing a unit normal vector. So let's go ahead and start with this question here. It says, find the tangent, the normal, and the curvature for the plane curve arc of t equals 9 natural log of secant of ti plus 9tj between negative pi over 2 to pi over 2. Why is it being restricted? Because remember that secant, it's going to have asymptotes, and we're just basically avoiding those asymptotes, which is my negative pi over 2 and positive pi over 2. So we're just thinking of the particle traveling between these two values in the parameter, so that we avoid the undefined values. So, to find the tangent, the first thing we need to do is we need to find the derivative of the position. So the derivative of natural log of secant of t, natural log of u, it would be u prime over u. That's the formula. So the derivative of secant of t, well, that's a constant. We're going to keep it there. But the derivative of secant of t would be secant of t times tangent of t divided by u, which is secant of t. Okay, and that's going to be my I component plus, and then the derivative of 9t would be 9, and that is my j component. Now we need to find the magnitude. Well, before we do that, we can simplify this, the secant of t. So the derivative of the position vector, or the derivative of the position of this particle, this plane curve, is going to be 9 tangent of ti plus 9j. Now, to find the magnitude, what we have to do is get the the squaring of the components, the square root of the sum of the square of the components. So it would be the square of 9 tangent of t would be 81 tangent square of t plus the square of 9 would be 81. And there's a few things we can do here. We can reduce it. The only thing we can reduce is that we can factor the 81 right here, and we're left with tangent square of t plus 1. Right? And then the square root of 81 is going to be 9, so that leaves us with this. Oh, and not only that, but remember that tangent square of an angle plus 1 equals to secant square of the angle. Okay? So that's the same thing as 81 times secant square of t. But the square root of 81 times secant square of t would just be 9 secant of t. So, let's go ahead and write now the unit tangent vector. The unit tangent vector can be found from the previous lecture by dividing the derivative of the position vector divided by its magnitude. So this is the position, the derivative of the position. So 9 tangent of t divided by its magnitude, which is 9 secant of t. 9 tangent of t divided by 9 secant of t, and this is my I component, plus the 9 divided by the magnitude, which is 9 secant of t, and that is my j component. This vector, unit tangent vector can still be reduced, because tangent is sine over cosine and secant is 1 over cosine. So 9 can be reduced right here, and tangent, like I said, is sine of t divided by cosine of t, and secant is 1 over cosine of t. Okay, and then plus, then right here secant of t is the same thing as the 9. It's going to give me 1 on the top over 1. So, and secant is 1 over cosine, so that's going to be the same as 1 over cosine of t, j. So my unit tangent vector is going to be, right here we flip this over, that's going to become sine of t divided by cosine of t times cosine of t divided by 1. Cosine can be reduced, so that leaves me with sine of t over 1. That's my I component, which is going to be just sine of t, I. Then 1 divided by 1 over cosine, we can flip that over, and that's going to be 1 times cosine of t over 1, and that's my j component, but that is just going to be the same as cosine of t, j. And this is the unit tangent vector. Now, we need to find the normal vector. To find the normal vector, we need to find the derivative of the tangent vector, and then we divide it by its magnitude. Okay, so first let's find the derivative of the tangent vector. So I'm going to put right here, this is the unit tangent vector. Okay. Now let's go ahead and the derivative of the unit tangent vector. So the derivative of sine of t would be cosine of t, and that's the I component, plus, and the derivative of cosine of t is negative sine of t, and that is my j component. Now we need to find the magnitude. Square root of, square the cosine, so that would be cosine square of t, plus, and then square the negative sine of t would be sine square of t. But remember that sine square of t plus cosine square of t is equal to 1, so the square root of 1 is going to give me 1. So And so the magnitude is 1 because remember, sine of t I plus cosine of t j, these parameters will create a, basically they travel along like a unit circle. So, and the unit circle means that the magnitude is 1. So that's what we found out right here. So now to find the unit normal vector, we're going to divide the derivative of the tangent vector divided by its magnitude. So the derivative of the tangent vector, it is cosine of ti plus negative sine of tj, but if we divide it by the magnitude of 1, it is basically going to be the same thing. Cosine of ti plus negative sine of tj. And this is the unit normal vector. Now, how do we find how much the particle or it's going to, or the graph of that vector, the position vector, how much is it going to curve at any point on the curve? Then to find that curvature, all we have to do is divide the magnitude of the derivative of the tangent vector divided by the magnitude of the derivative of the position vector, which is the derivative of which is the velocity vector. We call it the velocity vector. Okay, but I'm writing it in terms of r prime of t and t prime of t. So let's get the magnitude of the tangent vector, which is 1 divided by, and the magnitude of the position vector. The magnitude of the position vector, we found it to be 9 secant of t. Okay. And the only thing we can do, we can leave it like this, or we can rewrite it. That would be the same as cosine of t, or 1/9 times cosine of t, or cosine of t over 9. But either way, it is the exact same answer. So at any point in the curve, this is going to tell us how much the graph curves at any given point along the curve, given any parameter t. So t equals to 0, t equals to pi over 2, t equals to pi over 4. So it's going to give us an approximation of how much the graph curves at any given point along the curve. Next, let's go ahead and do the same thing here. Find the tangent, the normal, and the curvature. So to find the tangent, we need to find first of all the derivative of the position vector. Okay, so the derivative of the position, so it would be the derivative of this component, which is 3i, and the derivative of the 6 is 0. The derivative of negative t cubed is going to be negative 3t squared, and that is my j component. Okay, so now we need to divide it by its magnitude, but we need to find the magnitude. So square root of 3 squared, which is 9, plus negative 3t squared, negative 3t squared squared. If I square the negative 3, becomes a 9. If I square the t squared, becomes t to the 4th power. And there's only a few things we can do here to reduce this. The only thing we can do is that we can factor a 9 right here. That leaves us with 1 plus t to the 4th power. And then we can get the square root of the 9, which is equal to 3. So that's the most we can do right here. So that would be 3 times the square root of 1 plus t to the 4th power. So to get the unit tangent vector, again, we need to divide the derivative of the position vector divided by its magnitude. So if I divide this, 3 divided by 3 square root of 1 plus t to the 4th, that's going to be my I component, plus, and then divide this by the magnitude, which is negative 3t squared divided by the magnitude, which is 3 square root of 1 plus t to the 4th, and this is the j component. And we can reduce this, the 3, so that's going to become a 1, and negative 3 and 3, so that becomes negative t squared. So the unit tangent vector is going to be given by 1 over the square root of 1 plus t to the fourth I plus then negative t squared over square root of 1 plus t to the fourth. Let me just correct that because it looks weird. J. And that is our unit tangent vector. Now, let's go ahead and find the normal vector. To find the normal vector, we need to find the derivative of the unit tangent vector and divide it by its magnitude. So the derivative of the unit tangent vector, so getting the derivative of this, the best thing that we can do is, because we have to apply the quotient rule. So the easiest way would be to treat it as a product. So before I get the derivative, I'm going to modify this function by this vector by moving the denominator to the top, because the square root represents a power of 1/2. If I just bring it over, it's going to be a power of negative 1/2. So that would be the same as 1 times 1 plus t to the 4 raised to the negative 1/2. I don't need to put the 1 in the front, so this is basically what it should be. 1 times 1 plus t to the 4th raised to the negative 1/2 I. But again, I don't need that 1 in the front. We can just take it off. And then it says plus, same thing here, that's negative t squared times 1 plus t to the 4th power raised to the negative 1/2 also. And that's the j component. I think it's going to be easier to get the derivative if it's a product rather than if it's a quotient, because the quotient formula is a little longer. So let's get the derivative of this unit tangent vector. So the derivative of using remember we have to apply the power rule but also the chain rule because we have a function inside. So we bring the power over, so that's negative 1/2 times 1 plus t to the 4th, and then subtract 1. Negative 1/2 minus 1 is negative 3/2. But then we need to multiply times the derivative of the inside. The derivative of this inside function, that's the chain rule. It would be 4t to the 3rd power. And that would be my I component. Plus, now for the j component, apply the product. So it would be the first times the derivative of the second. So we get negative t squared times the derivative of this using the power rule. It would be bring the negative 1/2 over, and then 1 plus t to the 4th power and subtract 1. Negative 1/2 minus 1 is negative 3/2. And then times the derivative of the inside, which is 4t to the 3rd power. And then plus the second times the derivative of the first. The second would be 1 plus t to the 4th raised to the negative 1/2 times the derivative of the first, which is negative t squared. That would be negative 2t. And this is going to be the j component. So right here, 4t cubed times negative 1/2 is the same as negative 2t cubed. And that is a negative exponent. What I'm going to do now, I'm going to bring it back to the bottom. That's the same as 1 plus t to the 4th raised to the positive 3/2 on the denominator. Just multiply these two. And that is my I component. And plus. Now let's look at the j component. On this one, we're going to have two fractions. The first one is negative 1/2 times negative t squared is going to be positive t squared over 2 times 4t cubed. So positive t squared over 2. So 4 divided by 2 is 2. T squared times t cubed will be t to the 5th. So that would be the same as 2t to the 5th power. And this is if it has a negative exponent, it's going to go to the denominator. That is the same as 1 plus t to the 4th power raised to the positive 3/2. And then, but we still have another fraction. Plus, this is going to be for the j component. Okay. Now negative 2t, and that one has a negative exponent, so it goes to the bottom. So that would be negative 2t over, and that would be the same as 1 plus t to the fourth power raised to the positive 1/2. And that would be the j component. I'm going to leave some space because I'm going to do a modification. It is not, it is better if we try to combine the components into one single fraction. So right here, to make them into one single fraction, we need the least common denominator, which would be 1 plus t to the fourth raised to the 3/2. So in order for me to have this as a 3/2 power, I need to multiply it by 1 plus t to the fourth to the 1 power, which is just 1 plus t to the fourth. I don't need to put the 1 power, because 1 plus 1/2 is going to give me that 3/2. So I need to do the same thing here. Okay, so that's going to help us combine these two fractions. So let's get, so my derivative of the unit tangent vector is going to be negative 2t cubed over 1 plus t to the fourth raised to the 3/2. That's my I component. Okay, that's my I component right here. Then, plus, right here we're going to combine these two fractions, so that would be 2t to the fifth. When I distribute this, negative 2t times 1 is minus 2t, and negative 2t times t to the fourth is minus 2t to the fifth. Everything over the same denominator, which is going to be 1 plus t to the fourth raised to the 3/2 power. And that is my j component. Okay. So we can combine like terms. You see that 2t to the fifth minus 2t to the fifth, they cancel. So we're going to end up with this. The derivative of the unit tangent vector, it is the same as negative 2t to the third over 1 plus t to the fourth raised to the 3/2 I plus, and we end up with negative 2t over 1 plus t to the fourth raised to the 3/2 power, and that is our j component. So that's the derivative of the unit tangent vector. Now to find the normal vector, we need to find its magnitude. So the next thing we're going to do is find the magnitude of this vector, which is the square root of the components. Negative 2t cubed squared, it would be 4t to the sixth power over 1 plus t to the fourth raised to the 3/2. If I square it, the half is going to get out of the way. It's going to reduce. So I'm going to be left with 1 plus t to the fourth raised to the third power. Plus, square the negative 2t, that would be 4t squared, over, square this, it would be 1 plus t to the fourth raised to the third power. And then I can combine them into one single fraction, so it's 4t to the sixth power plus 4t squared, everything over 1 plus t to the fourth, everything raised to the third. But then you see that on the numerator, we can, I'm going to try to see if I can reduce it. We can factor a 4t squared. If I factor the 4t squared, we're left with t to the fourth plus 1 over 1 plus t to the fourth raised to the third. This is the same as this, right? So that's 1, that's 3. So I can reduce this with one of these, so we're left with 2 on the denominator, right? So that equals to the square root of 4t squared over 1 plus t to the fourth to the second power. Now we can get the square root. The square root of 4t squared would be 2t, and the square root of 1 plus t to the fourth to the second, the square root of that would just eliminate the second power, leaves me with 1 plus t to the fourth. So that's the derivative of the unit tangent vector, the derivative of the unit tangent vector. So to get the unit normal vector, we need to divide the derivative of the unit tangent vector divided by the magnitude. So derivative of the unit tangent vector is this. We're going to divide it by the magnitude, which is this. So we're going to get negative 2t cubed over 1 plus t to the fourth raised to the 3/2 divided by the magnitude, and the magnitude we found it to be 2t over 1 plus t to the fourth. That would be my I component, plus, and then the derivative of the unit tangent vector, which is this on the j component. This is the I component, which is going to be negative 2t over 1 plus t to the fourth raised to the 3/2 divided by the magnitude, which is 2t over 1 plus t to the fourth, and that is the j component. We can reduce this, flip the fractions, and multiply. Right? So that will leave us with the following. Negative 2t to the third over 1 plus t to the fourth raised to the 3/2 times the reciprocal of the bottom, which is 1 plus t to the fourth over 2t. That's the I component. Plus, and now for the j component, it would be negative 2t over 1 plus t to the fourth raised to the 3/2 times 1 plus t to the fourth divided by 2t. And that's the j component. Okay. Now, let's reduce this. So my unit normal vector is going to be equal to, what can we do here? You can see that we can reduce, this is one of these with one of these. I don't want to do this right here, and I'm going to be left with a 1/2, because that's 1 and that's 1.5, so we're left with 1/2 on the denominator, right? And then also the the 2 reduces with the 2 right here, so we're left with 1, and the t cubed with the t, so we're left with t squared, right? So we're going to end up with negative t squared over 1 plus t to the fourth raised to the 1/2 power. Or when we say 1/2 power, that is the same thing as the square root of 1 plus t to the fourth. That's going to be my I component for the unit normal vector. Plus, now let's find the j component. Right here, what can we do? Let's see. So 2t and 2t can be reduced, so we're left with 1. And also, not only that, but this can be reduced with one of these, so we're left with a 1/2 on this one, the denominator. So on the numerator, we are left with a -1, right? Because that's a negative, I forgot, right here. So -1 over, then 1 plus t to the fourth raised to the 1/2 is the same as the square root of 1 plus t to the fourth. And that is our j component. And this gives us our unit normal vector. Next, to find the curvature at any point on the curve, now that's the last question we need to find. To find the curvature, we need to divide the magnitude of the unit tangent, the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative of the position vector. So the magnitude of the derivative of the unit tangent vector was this, 2t over 1 plus t to the fourth. And the derivative of the magnitude of the derivative of the position vector, it is right here. The magnitude of the derivative of the position vector was 3 times the square root of 1 plus t to the fourth. So this is over 1, so then to simplify this, I'm going to multiply by the reciprocal, so it would be 2t over 1 plus t to the fourth, multiply times 1 over 3 times the square root of 1 plus t to the fourth. And 2t times 1 is going to be 2t over, then it's going to be 3, and when I multiply the 1 plus t to the fourth times the square root of 1 plus t to the fourth, this is 1 plus t to the fourth raised to the 1/2 times the 1 plus t to the fourth raised to the first power 1 plus the 1/2, it would be 3/2. So that will give us a 1 plus t to the 4th raised to the 3/2. And this will give us at any point along the curve, at any value of t, it's going to give us what is called the curvature of the position vector. Next, let's do the same thing for this problem. Find the tangent, the normal, and the curvature. So the unit tangent vector, the principal unit normal vector, and the curvature. So for the tangent, we need the derivative of the position. So the derivative of 9 sine of t would be 9 cosine of t. That is my I component. The derivative of 9 cosine of t would be negative 9 sine of t. That is my j component. And the derivative of 12t would be 12. And that is my k component. Now we need to find the magnitude. That would be the square root of. Square this component, it would be 81 cosine square of t, plus square this component, it would be 81 sine square of t, and square this component, it would be 144. Okay. But let's remember that this, I can factor the 81, and that leaves me with cosine square of t plus sine square of t. I can factor the 81 from the first two terms, and then plus 144. And by doing this, I'm doing it because cosine square plus sine square equals 1, so that leaves me with 81 times 1, which is 81. So that is the same as the square root of 81 plus 144, and that would be 225, so it would be the square root of 225, and that would be 15. So, to get the unit tangent vector, we divide the derivative of the position divided by its magnitude. So it's going to be 9 cosine of t, which is the derivative right here on the I component, divided by the magnitude, which is 15, I, plus, and then the j component of the derivative, which is negative 9 sine of t, divided by the magnitude, which is 15, that is j, plus, and then 12 divided by 15, and that is my k component. We can reduce this. So the unit tangent vector is going to be 9 over 15 can be reduced to 3/5. So it will be 3/5 cosine of t, that is my I component, plus, and that's the same but negative 3/5 sine of t, that is my j component, plus, and right here it would be 4/5 k, and that is my k component. So this will give us the unit tangent vector at any point in the curve. Next, let's go ahead and find the normal vector. So we need to find first the derivative of the unit tangent vector. So the derivative of 3/5 cosine of t would be negative 3/5 sine of t. That's the I component. The derivative of negative 3/5 sine of t would be negative 3/5 cosine of t. That is our j component. And the derivative of 4/5 is going to be 0. Then we need to divide it by its magnitude. So let's find the magnitude. Square root of, square this component, square 3/5 squared is going to be 9 over 25, and if I square sine would be sine square of t, plus square this component, it would be 9 over 25 cosine square of t, and then square the k component, that would be plus 0 squared, which is 0. So we're left with just the sine square and cosine square. So I can factor the 9 over 25, and we're left with sine square of t plus cosine square of t, but sine square plus cosine square equals to 1. So 1 times 9 over 25 will just be 9/25. But the square root of 9 over 25 would just be 3/5. So To find the unit normal vector, we need to divide the magnitude of the derivative of the tangent vector divided by its magnitude. So this component divided by the magnitude 3/5 is going to give us negative 3/5 sine of t divided by the magnitude, which is 3/5. That will be the I component, plus then we have negative 3/5 cosine of t divided by the magnitude, which is 3/5. That is our j component. And then plus 0 divided by 3/5. That is our k component. So our principal unit normal vector is going to be, this reduces, so that leaves me with negative sine of t. That's my I component. Plus, this reduces, so that leaves me with negative cosine of t. That is my j component, plus 0k. So this will be our principal unit normal vector. Remember, the unit normal vector is the vector that goes inward towards the circle of curvature, towards the radius of the circle of curvature at any given point in the curve. Next, let's go ahead and find the curvature. To find the curvature, we need the magnitude of the derivative of the tangent vector divided by the magnitude of the derivative of the position vector. So the magnitude of the tangent vector, the derivative of the tangent vector was 3/5 divided by the derivative of the position of the magnitude of the position vector. The magnitude of the position vector was, the derivative of the position vector was 15. So over 15. And that's over 1. So we're going to have 3/5 times 1/15. And we can reduce 3 and 5. That's going to be 1/5. So that would be 1 over 25. I want you to make one, let's see. Give me 1 second. One little observation. Basically, what this 1 over 25 is going to represent, that 25 on the denominator, it will represent the radius of the circle of curvature, not just the curvature is 1/25. That's how much the graph is curving, but the circle of curvature at that given point, it's going to be right here 1/25. And the reason that it is a constant, because this is a particle. Remember, these components tell me that this particle is traveling along a circle. Okay, so the circle of curvature at any point on the circle will be basically the same, because it is curving constantly about the same amount. That's why the curvature was a constant right here in this case. So in the circle of curvature, I wanted to talk about it in this question since it is just a constant. That radius, that denominator of this curvature will be the radius of the circle of curvature at any given point on this particular curve. Okay, so that gives us another definition here, that the curvature is going to be the same as 1 divided by the radius of curvature. Of circle of curvature. Okay. Next. Now I guess we got the point for these. Okay. We're gonna skip over to these following questions. Now on this, when we are given a function, okay, and we want to find basically how the curvature at any given point on a given function, then we can either parameterize the function. That is one thing we can do, and then do what we just did on the previous questions, or we have a different formula that we can use when we are finding the curvature of a function in terms of x. And the formula is the following. The second derivative of the function, the magnitude, the second derivative of the magnitude of the function divided by 1 plus the first derivative of the function squared, everything raised to the 3/2. So there's a couple of things that we need to find first. We need to find the first derivative, the second, the magnitude of the second derivative, and then the magnitude of the second derivative. So this is the function we're looking at, and we're trying to find a function of the curvature at any given point on this parabola, 7x squared. So first of all, let's get the first derivative. The first derivative of this function would be 14x. The second derivative of this function, it would be 14. And the magnitude of this second derivative, it is just the square root of 14 squared, which is just going to be the same. It's going to be 14 because it's just a constant, right? Okay, so we got all the information we need. So to find the curvature in terms of x, the second derivative, the magnitude of the second derivative, which is 14, divided by 1 plus the first derivative square, 14x squared, it's going to be 196x squared, and everything raised to the 3/2. And this gives us the function of how the graph is curving at any given value of x along the parabola. I'm going to show it to you in the graph because we have to do that next. So I'm going to kind of make it a little bit large so we are able to see the things that I'm going to show you next. So I'm going to try to make extra lines there. Let's first of all grab the function 7x, is it 7? Yeah, 7x squared. So when x is equal to 0, y is 0. When x is equal to negative 1 squared is 1 times 7 is going to be 7. Right? 1, 2, 3, 4, 5, 6, 7. When x is positive 1, y is also 7. When x is negative 2 squared is going to be 4. 4 times 7 is going to be 28. So this is basically going to be all the way up. So we're not going to be able to see that point. Also this one, we're not going to be able to see it. So this is the graph of the parabola between negative 2 and positive 2. Right? Something like that. And then also on this side, this is what we're going to see. Okay. So now I want you to analyze the curvature, and just so that you understand it, this function of the curvature that we used right here, let's use some values of x and find k of x so you can see what happens at any point on the curve. So substitute it with negative 2, negative 1, 0, 1, and 2. This is just those values, those 5, and see what happens. So I'm going to open the calculator just to make it faster. So if I replace negative 2 into this curvature function, we're going to have 14 over parentheses 1 plus 196 and then times x and the x is going to be -2 squared. So I'm just going to put it in parentheses instead. -2 squared. And then that is going to be raised to the power of 3/2. And look what that is. What does that mean right there? That means 4 decimal places to the left. So that means 0.000636. Let's just put 0.0006. What about at -1? So now I'm going to change that x to a -1 right here. Look at what it is, 0.005. What about 0? $14. What about 1? .005, you see what happens? And 2 is going to be 0.0006. What do you notice? Where is it that this function is curving the most? It is curving the most right here in the middle, right close to 0. Where is this function curving the least? Right on the edge. Right here is we can almost say that it is vertical, right, at these edges. As it approaches 0, the graph is starting to curve more and more from both the left and from the right. That's what this function is telling me right here, that the curve, the value for the curvature is almost going to be 0 at -2, is almost going to be 0 at -1, but and also at +1 is almost going to be 0, and at +2 is almost going to be 0, but as it approaches 0, the curvature is going to go all the way to a curvature of 14. So it's going to, right here is where the graph is starting to curve more and more and more. So we say that the curvature function is telling me right here that right here through the middle it is curving the most. So this is a function of the curvature. So it's telling me how much of the function is curving at any point along the curve. So as we get away from 0, the function is curving less and less and less. Same thing happens as we get far away from 0 on this side. Okay, so this function represents the curvature, how much the graph of this function x7x squared is curving at any given point on the curve. Now on this one it would be basically the same thing. Okay, let's talk about the last thing, circle of curvature. Now for the circle of curvature, this is the next thing we're going to do. We're going to be finding an equation for the circle of curvature at any point along a given curve. Okay, just remember that one thing is that we need the normal vector, because the normal vector, when I multiply times the magnitude of the radius, is going to give me the length from the given point all the way to the radius of the circle. And basically that's going to help us to identify what this point, the center of the circle, is going to be. In order for us to find the equation of a circle, we need the center of the circle, because remember that the equation is going to be x squared plus, well, I'm going to write it in terms of when the center is not in the origin. It would be x minus some point x of 0 squared, where that x of 0 and y of 0 would be the center, right? Plus y minus y of 0 squared equals to the radius squared. But remember one thing, that the radius is the same as 1 over the curvature. So it would be 1 over the curvature squared. That's going to give us the radius squared. Okay, so we need to find the radius of curvature by doing the 1 over the curvature, because that would give us a radius, remember? And we need to find the normal vector and multiply times the magnitude time, which is the radius, to get basically to be able to locate the center, or the center of the circle, and then we can write the equation for that circle of curvature. Okay? Let's do this application in this problem here. Find the equation of the circle of curvature of the curve r of t equals 6ti plus sine of tj at the point 3 pi comma 1. Now one thing that it tells me here is that it is at the point 3 pi comma 1, but we need to find out what value of t, which is the parameter, does that happen. So this is my I component. We can use the 3 pi to find the t from the I component, because this is the position, the x position, and the position is this function. This is the position function, right? And this is the starting position of the we want to find the curvature at this point, so that's the position. So at 6t, the position of that component is 3 pi, or at sine tj, the position is going to be 1. That's my y component or my j component. Okay, so we can set either one to find the value of t of the parameter where we want to find the curvature of. So we can say 6t either equals to 3 pi, or we can say sine of t equals to 1 and then solve for either or. I think it's easier just to solve for this one, right? Either one is going to give us the same result. So if I divide by 6, that would be 3 pi divided by 6. So the parameter t, it is exactly at t equals to pi over 2, where we have the position 3 pi 1 in this particle. Let's keep this in mind because we're going to use it later, because that's at the exact position that we want to evaluate our normal vector, which is what's going to help us to determine the circle of curvature. All right, to be able to get the normal vector, we need to find several things. We need to find the tangent vector, we need to find the unit tangent vector, and then the derivative and its magnitude to be able to get the unit normal vector. Okay, so there's a little scratch work to do before we can get to that point. So let's first of all find the derivative of the position vector. That would be the derivative of 6t is 6i, plus the derivative of sine of t would be cosine of tj. And then we need to find the magnitude. That would be the square root of 6 squared, which is 36, plus the cosine square of t. And that's the magnitude. So then the unit tangent vector, we need to divide the derivative of the position divided by its magnitude. So it would be 6 over the square root of 36 plus cosine square of t I plus cosine of t over the square root of 36 plus cosine square of t, and that is my j component. So, but this is not it. This is just the unit tangent vector. We need to get the normal vector. So to get the normal vector, we need the derivative of this tangent vector. But again, since that's a quotient, it is easier to make it a product. So we can apply the product rule. So I'm going to move this. This is the same as power of 1/2. So I'm going to move it to the top as a negative 1/2. So that would be 6 times 36 plus cosine square of t raised to the negative 1/2 power. That is my I component. Plus, I'm going to move that one also to the top as a negative 1/2. 36 plus cosine square of t raised to the negative 1/2. That's my j component. So let's find the derivative of this unit tangent vector. So the derivative, this is just a constant, so we just need to use the power rule and also the chain rule to get the derivative of this guy. So the derivative would be, move the power to the front, negative 1/2, and then subtract 1 from the power of this 36 plus cosine square of t. Negative 1/2 minus 1 is negative 3/2, but then multiply times the derivative of the inside. The derivative of the inside is 2, the derivative of cosine square, apply the power again, 2 cosine of t. But then the derivative of the cosine, so we can do the chain rule, which is negative sine of t. And all of this will give us the I component. Plus. Now, For the j component, we're going to do the same. We're going to apply the product rule. The derivative of the first times the second. So the derivative of cosine would be negative sine of t times the second, which is 36 plus cosine square of t raised to the negative 1/2. But then plus the derivative of the first times the second plus the second plus the derivative of the second times the first. So it will be plus cosine of t times the derivative of this guy. So the derivative of this, I need to apply everything we applied on the first one. Move the power to the front, which is negative 1/2. Subtract 1 from the power. So it would be 36 plus cosine square of t. Subtract 1, so it would be negative 3/2. Right? And then times the derivative of the inside. The derivative of 36 is 0. The derivative of cosine square would be 2 times cosine of t, but then times the derivative of cosine, which is negative sine of t. And that will give us the j component. Now, let's go ahead and first reduce the I component. Negative 1/2 times 2 is negative 1, times the negative is positive 1, times 6 is positive 6, sine times cosine, right? So it would be 6 sine of t, cosine of t, and then times this raised to the negative 3/2, that's the same thing as just divided by 36 plus cosine square of t raised to the positive 3/2. And that would be the I component. Plus, let's do now the j component on the right side. Now, let's first of all look at the first guy. Negative sine of t times this. Since this has a negative 1/2 power, I'm going to move it to the bottom. So that would be negative sine of t divided by 36 plus cosine square of t raised to the positive 1/2 power. Plus, the j component is going to be long. So now let's simplify this right side. What do we simplify first? Negative 1/2 times 2 is negative 1. Negative 1 times a negative is positive 1. Sine times cosine, it would be positive 1 sine of t times cosine square of t. Because cosine times cosine is cosine squared. And then times this guy raised to the negative 3/2, that's the same thing as just dividing by 36 plus cosine square of t raised to the positive 3/2. I'm going to leave some space because, like I said, we're going to do the same trick on this guy right here. In order for me to simplify that, since we have two fractions, I want to make them into one. I want to make them the same denominator. So right here, well, I think the one that needs to be multiplied is not this one, so it wouldn't matter in this case. So I don't need the space for this guy. This is the one that needed the space. So if I want to make the same denominator, I need to make this a 3/2 by just multiplying the 36 plus cosine square of t here on the denominator and also on the numerator. Because 36 plus cosine square of t to the first power times 36 plus cosine square of t to the 1/2 power at the powers, 1/2 plus 1 would be 3/2, which is the same as this denominator. So let's simplify this. So the derivative of the unit tangent vector is 6 sine of t cosine of t over this guy, 36 plus cosine square of t raised to the 3/2 power. That's my I component. Plus, now the j component. When I distribute this guy, negative sine of t times 36, it would give us negative 36 sine of t. Negative sine of t times cosine square of t would be minus sine of t cosine square of t. Then plus this guy right here, which is sine of t cosine square of t, everything over the same denominator, which is 36 plus cosine square of t raised to the 3/2 power. And that is my j component. So then this is what the final thing of my derivative of the unit tangent vector is going to be. 6 sine of t cosine of t, still the same, over 36 plus cosine square of t to the 3/2 I, plus, and look what happens here, negative sine square of t negative sine of t cosine square of t plus sine of t cosine square of t, they cancel, so we're left with negative 36 sine of t over 36 plus cosine square of t raised to the positive 3/2 nj. And that is the derivative of the unit tangent vector. Now we need to get its magnitude, to get the normal. So, the magnitude of this. So, we're going to get the square root of, we're going to square this component. 36 squared is going to be 36. Sine square would be sine square of t. Cosine square would be cosine square of t. Since they have the same denominator, everything's going to be over the same thing. So I'm going to put that denominator on the whole thing. When I square the 3/2, it's just going to become a third power. The half is going to disappear. Right? So it's just going to be 36 plus cosine square of t to the third power. Then, on this guy, when I square it, 36 squared, I'm just going to put it like this. 36 squared. I'm not going to square it because for one reason. Then I square the sine, it's going to become a sine squared. I'm not squaring it because I'm going to factor. Because remember, we still need to kind of simplify this. So I can factor a 36 from both and a sine squared. If I factor this, we're going to be left with cosine square of t plus another 36 right there. Right. And that's over 36 plus cosine square of t to the third power. We can reduce this guy with one of these guys, so we're left with a second power on the bottom. So we're left with this. The square root of 36 sine square of t divided by 36 plus cosine square of t raised to the second power. When I get the square root of 36 sine square of t would be 6 sine of t. Then, when I get when we get the square root of this square, is just gonna reduce the square, so that's 36 plus cosine square of t. Okay. So this is the magnitude of the unit derivative of the unit tangent vector. So to get the normal vector, we need to divide the tangent vector divided by the magnitude. So divide this, first of all, let's divide the I component. It would be 6 sine of t cosine of t over 36 plus cosine square of t to the 3/2 power. Then we're going to divide it by the magnitude of that unit tangent vector. And the magnitude was 6 sine of t over 36 plus cosine square of t, and that is the I component, plus then the j component. Divide the j component by the magnitude, so it would be negative 36 sine of t over 36 plus cosine square of t raised to the 3/2 divided by the magnitude, which is 6 sine of t over 36 plus cosine square of t. But when we divide, remember, a fraction by fraction, we multiply by the reciprocal, so then we're going to reduce it to this. So multiply 6 sine of t cosine of t over 36 plus cosine square of t to the 3/2 multiplied by the reciprocal of this, which is 36 plus cosine square of t over 6 sine of t. That will give us the I component, plus, same thing here, multiply this fraction by the reciprocal of this one, so it's negative 36 sine of t over 36 plus cosine square of t to the 3/2 times 36 plus cosine square of t over 6 sine of t. Okay. And that will give us the j component. So now let's go ahead and reduce this to get the unit normal vector. Remember, this is the one that's going to help us to find the center of the circle of curvature. So let's reduce this. The 6 sine of t reduce, and also one of these with one of these, so that's 1.5, so we're going to be left with 1/2 on the denominator. Same thing here. Sine of t and sine of t reduces. Negative 36 divided by 6 is going to give me a negative 6, right? And one of these with one of these, so that's 1.5, so that leaves me with 1/2 on the denominator. So what are we left with? On this, we're left with cosine of t over 36. Now, that 1/2 is just going to mean the square root, so I'm going to change it back now. Cosine of t over the square root of 36 plus cosine square of t, that's my I component, plus, then on this one it's a negative 6 over, then that 1/2 means also the square root of 36 plus cosine square of t, and that is my j component. So this is the principal unit normal vectors. That's going to help us to find the circle of curvature. Okay, so what do we need now? We need to find the curvature, because in order for us to find the radius of the circle of curvature, we need the curvature at that given point. So to find the curvature, we need to get the magnitude of the unit tangent of the derivative of the unit tangent vector, which is this guy right here, divided by the magnitude of the derivative of the position vector, which is this guy right here. Okay. So I'm going to first of all do that, and then I'm going to evaluate it at the value of t that we found. This is going to be the last thing we're going to do, evaluate them, okay, at pi over 2. Because that's when the particle is at this position, at the parameter t equals to pi over 2. Okay, so first of all, let's divide the magnitude of the derivative of the tangent vector, which is going to be 6 sine of t divided by 36 plus cosine square of t. So the curvature, the magnitude of the derivative of the tangent vector divided by the magnitude of the derivative of the position vector. So it was, I forgot it, 6 sine of t, correct? 6 sine of t divided by 36 plus cosine square of t, and that over the magnitude of the derivative of the position vector, which was the square root of 36 plus cosine square of t, and that is over 1. So when I divide a fraction by a fraction, I multiply by the reciprocal. So that would be 6 sine of t over 36 plus cosine square of t times 1 over the square root of 36 plus cosine square of t. Remember that the square root of cosine square of t means 36 plus cosine square of t to the 1/2 power times 36 plus cosine square of t to the 1 power. I just add the powers. That is going to be the same as 36 plus cosine square of t. 1 plus 1/2 is going to be 3/2. And then on the top, 6 sine of t times 1, it would be 6 sine of t. This is going to give us a curvature along any given value of t. But now we want to find the curvature. This is going to be in terms of the parameter t, I forgot. But now we need to find the curvature at the t equals to pi over 2. So it would be 6 times sine of pi over 2 divided by 36 plus cosine square of pi over 2 raised to the 3/2. Sine of pi over 2 is going to be 1. So it's going to give us 6 times 1 over cosine of pi over 2 is going to be 0. So that gives us 36 plus 0 squared, and that raised to the 3/2. 6 times 1 is 6 over 36 plus 0 is 36. 36 raised to the 3/2 means the square root of 36, which is 6, and then raised to the third power. That means 6 times 6 times 6, so that would give us 1 divided by 6 squared, which is 36. If we reduce the powers here, that gives us a 2 on the denominator, 6 squared, which is 36. So 1 divided by 36, so this is our radius, so that means that the radius of the circle of curvature at that given point, it's going to be 36. Remember that the curvature is the same as 1 divided by the radius of curvature. Okay. Now, in order for me to see how far the normal vector goes, I need to multiply times the magnitude. So magnitude times its direction, in other words. First of all, let's find the direction in which it's going at pi over 2, first of all. Going with the normal, right here. At the direction that it's going at t equals pi over 2. So it's going to be cosine of pi over 2 divided by the square root of 36 plus cosine square of pi over 2 I plus, and then the j component says negative 6 over the square root of 36 plus cosine square of pi over 2, and that is my j component. So cosine of pi over 2, we said it was 0. So it does, and so that's 0 divided by 6, which is going to be 0, so that's 0i. And that negative 6, and then cosine of pi over 2 is 0. 0 squared is 0, plus 36 is 36. The square root of 36 is 6. So that gives me negative 6 divided by 6, which is negative 1j. This is the unit normal vector at that given point, 3 pi, comma, 1. But in order to see how far it goes, we need to multiply times its magnitude. In that magnitude, we're talking about the radius. Okay, times the magnitude of the radius, because we want to know how far is it going to go towards the center of the circle. Okay, so if I multiply that normal vector times the radius, it's going to be 36 times that normal vector at the point pi over, at the t equals pi over 2. It's going to be 0 times 36i plus negative 1 times 36j, and that is going to give us 0i minus 36j. Okay, so but the initial position of the initial position where we want to find the curvature of is at 3 pi comma 1. That's the point. So we're going to add, this is the point 0 comma negative 36. So add those 2 points, and that will give us the center of the circle of curvature. So plug the initial position. Okay, so the initial position is 3 pi, yeah, comma 1. Okay, so if I add them, then the center of the circle of curvature is going to be 3 pi, 0 plus 3 pi is 3 pi, comma, negative 36 plus 1 is negative 35. This is the center of the circle of curvature, and we found the radius r to be 36. That's the center, that's the radius. So let's go ahead and write the equation of the circle of curvature. It's a little bit slow. Let me see. Equation of circle of curvature. X minus x of 0, which is my 3 pi, square, plus y minus y of 0, which is negative 35, square, equals the radius, which is 36, square. This is going to change to a plus, so my equation is going to be x minus 3 pi square plus then y plus 35 square equals, and then 36 square, it's going to give us 1296. And this is the equation of the circle of curvature. It is located at this center, 3 pi comma negative 35, and it has a radius of 36. I'm going to show you now basically how this would look like. Looks like a very large circle. Why is it that this is going to give me such a very large circle? For the following reason. Let's take a look at the graph of, this tells me that this curve is parametrized, is the parametrization of the graph of y equals sine of 1/6 x. Okay? Any point on this curve will be basically the same as the points on this curve in the xy plane. So let's take a look at how this graph looks. Sine of 1/6x. I'm going to go to the right side. Or maybe I can put it on a new page right here. Okay. Remember that sine has a period of 2 pi, right? But this one, remember, this enlarges the period when I have a number in front of the x. So, and the formula for the period, it is 2 pi divided by b. This is the value of b, which in this case is 1/6, right? So if I divide 2 pi divided by 1/6, that's going to be 12 pi. Okay, that's a big period. Okay, so I'm going to do this. I'm going to create a very small graph. Okay. So the period, it tells me that it's going to be 12 pi. Okay, so I need to divide it into 4 to get the interval, right? So to get the interval for each point. So 12 pi divided by 4, it's going to give me 3 pi. So every value is going to be 3 pi. And how much is 3 pi approximately? Like in radians, it is 9.42. So I just want to make it as exact as possible. So every 3 pi is 9.42, so it's going to be like 9 of these units, approximately. So that approximately we can say that 9 units will be like, let's say right here. So that's 3 pi. Then it goes to 6 pi. Then it goes to 9 pi. And then it goes to the period, which is 12 pi. Remember that the graph of sine starts from 0. Then right here the amplitude is 1 because the value in the front is 1. Then it goes to the amplitude, the highest value, which is 1. then it goes back to 0, then it goes down to -1, and last it goes back to 0. So this is what one period of the graph of this sine function will actually look like, approximately. What do you notice about the curvature at any given point on this curve? The curvature is very small anywhere on the curve. Yes? So that means, just like I told you at the beginning of the section, the smaller the curvature on the function is, the bigger the circle of curvature that you're going to have. So what we're trying to look at is we're trying to look at the circle of curvature exactly at this point, 3 pi, comma 1. That's the point that we were given at the beginning, 3 pi, comma 1. And according to the definition, what was the normal vector that we found? Go back and take a look at it. The normal vector that we found was 0i, well, the original unit normal vector, 0i minus 1j, right? You see that the circle of curvature, the circle is going to go down here, the center of the circle, right? So 0i minus 1j, so it is going in this direction. But like I said, since we're trying to find the radius, we need to multiply times the radius. That's why we multiplied the normal vector times the radius. And that gave me the point 0i minus 36j. 0i minus. So since it is 0i minus 36j, that goes towards the radius. Just think of it like this. 0i minus 36j all the way down. And that is going to go all the way to the point. We found the point on the previous slide. It's going to go all the way down to the point where we extend that vector 0i minus 36j from here. It's going to go to the point 3 pi minus 35 when we 3 pi and comma negative 35. So that's where it's going to go. So 3 pi and all the way down to negative 35. So I'm going to try to sketch it as closely, as accurate as possible so you can see. I don't know how far I can go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 30, 1, 2, 3, 4. Let's say this is negative 35. So this is basically where the center of the circle of curvature is going to be. So just imagine a big, huge circle that is going to be right here, that is going to be basically touching this curvature at that point. I'm going to try to sketch it so we can see that. So I want to see that point there. And that's basically what the circle of curvature at that point will actually tell us. Do you see? And that looks exactly like a circle with and the center. It looks to be that point that we just grabbed. Okay. So, and that graph of that equation basically, since it has the center of 3 pi comma negative 35 with a radius of basically 36 units. Okay, because from that center all the way here, that would be 36. Remember that we said that from 3 pi to 6 pi is about 9 units. 9, 9, 9. So basically it's 9 and something. So once it reaches all the way right here, which is the edge of the circle, it should be about 36 units long. Okay, so and that circle has an equation of x minus 3 pi squared plus y plus 35 squared equals the radius squared, which is 1296. And that's the circle of curvature right at this point. Will the circle of curvature be the same right at this point? 9 pi, comma, -1. The equation will not be the same. The radius will be the same because the curvature at this point is exactly the same as the curvature at this point. So the curvature are the same, so that means that the circle will be the same size. However, it will not be located at the same position. It will not be at the same center. The center on the circle at this point, it would be up on the positive, on quadrant 1. Okay? So this basically concludes section 12.4, which is about curvature.